So welcome to lecture 30. So in the last class, we saw how second law of thermodynamics was used in getting more information about the constitutive relation. And that was in a specific context of compressible inviscid fluid. Okay. So today we are going to look at from a more general perspective. But again, focusing only for thermoelastic material, any kind of thermoelastic material. Okay, that means we are not talking about elastoplastic material or viscoelastic material. So thermoelastic means it covers purely elastic materials as well as materials which have their properties changing when you change the temperature. Okay, but still elastic. Now you have seen that in your balance equations, what are the unknowns for which we actually need the constitutive equations. So if I just list them, you have sigma, you have the specific internal energy, then you have heat flux vector, and you have specific entropy, right? Or equivalently, you can also think of first Piola-Kirchhoff stress tensor or Helmholtz free energy or the referential heat flux vector and then again the specific entropy, right? And so we are looking for the functions for them, isn't it? So that's why I put a hat above. So this hat above is not to be confused with that it's a Lagrangian function. It's the hat is just to denote that it's a function here. Okay, it has not got to do with the fact that it's a Lagrangian variable. Okay, now we have to now postulate what will these functions depend on in the context of thermoelastic material. Okay, so one is of course I think all of you can see that it's temperature should figure out, right? Temperature should be there in the argument because we know that with temperature properties change. So let's put temperature in there. So temperature I have already written, position and time. Well, not explicitly on time, unless the material is degrading with time. We should not write explicit dependence on time. Okay, but position, yeah, yes, position, you're right. So y hat, okay. Anything else? See, for the heat flux, what kind of relation you have seen in your undergraduate course? And this heat flux within the body is actually due to conduction, right? It's due to conduction that the heat flows within the body. So conduction is proportional to what? Temperature gradient, right? Yes. Well, thermal conductivity is the material constant, but what variable does it depend on? It depends on the temperature gradient. So you have rightly figured out that temperature gradient should somehow be present, isn't it? So Let's put that here for the heat flux temperature gradient. But then, yesterday we talked about equipresence. If it is there in one of the variables, let's put it in all the variables. Okay, so we are going to put it everywhere. So likewise on the other side, we can have the Lagrangian gradient, for example. Okay, so I'll say grad x theta, grad x theta, grad x theta. Now about the position dependence, can you say something more about it? Can it really depend on position? For example, just think of a body which you translate. Okay, just think that we are translating the body in space. Rigid translation. So you have a body over here and you rigidly translate. So the position here is y and you rigidly translate it to make the position y plus t, where t is the translation vector constant. Do you think that any of the properties will change? Will any of the properties change when you translate the body? Will the stress change in the body? Will internal energy, specific internal energy change? Will the heat flux change? Will eta change? The answer is obviously no, right? So therefore, it means the dependence on position, although it's a more quite general thing, but it's actually not going to depend on position. It's going to depend on something related to position, of course, but not on the position directly. So what do you think? Can we modify it to something? So if you make the dependence on gradient of y, then you see that gradient of y is same as gradient of y plus t, because t is constant. So the dependence should actually be on the gradient of y, isn't it? Not on y itself. So therefore we can go back and remove y from everywhere and make it gradient of y, which is actually the deformation gradient tensor, big F. Okay, so that's all the arguments that we can think of for thermoelastic materials. Of course, people coming from fluid mechanics, you would say that should it not also depend on strain rate? So we'll talk about that later on. So that does not come under this thermoelastic material. Then of course, if you have viscoelastic body, then also it depends on strain rate. If you have plastic materials, elastoplastic, then it has some internal variable dependence also. So we are not talking about such things. Okay. Having put this dependence, now we have to think of um, what restrictions, for example, will the field equations put in. And you know that if you talk of field equation, then you have second law of thermodynamics, the entropy inequality to begin with. Maybe we can test from there. Is it going to put any restriction? Okay, so let's start from there. And we can work with the Lagrangian form. So the second law of thermodynamics, or the entropy inequality, has the following form: rho naught psi dot minus P double contraction F dot plus rho naught eta theta dot plus heat flux vector Q naught dot grad x theta divided by theta, and this is less than equal to 0. Okay, so let's now substitute the functional forms for psi, eta, and everything. So you see, we need psi dot. Now this is the dependence on psi. So what will be psi dot? You take the derivative with respect to each of the argument, then the derivative of the argument with respect to time, right? So if we do that, this is going to become rho naught del psi del f double contraction f dot plus del psi del theta times theta dot, right? Plus del psi del so grad theta, let's call it a vector g, for example. Okay, so I am calling g is equal to grad x theta, and then dot with g dot, right, which is grad x theta dot, and g dot is then same as grad x theta dot. Okay, you can interchange the order of derivative because x and time are independent, and then you have the remaining things then minus p double contraction f dot plus rho naught eta theta dot plus q naught dot grad x theta divided by theta less than equal to 0. Okay, this has to be satisfied for all thermodynamic processes. So it's going to put really a very strong restriction on the constitutive form, as you will see. And you have seen some of it yesterday also. So now let's, club the time derivatives, the terms corresponding to time derivatives of different variables together. So for example, f dot, club the things corresponding to f dot together. So you have rho naught del psi del f minus p double contraction f dot. Okay, likewise for the ones corresponding to theta dot, you have rho naught del psi del theta plus eta times theta dot. Then you have rho naught del psi del g dot g dot, and finally q naught dot grad x theta over theta dot being less than equal to 0. Okay, now you see what are the variables here. We have f present here, we have theta present here, we have grad theta present here, and also their time derivatives. Which is f dot theta dot grad x theta dot. Now it turns out now you can choose arbitrary values for f theta and grad x theta. And for once you choose that value, you can also choose different rates. You can choose arbitrary rates. For a given, so for at a given time, you can have some f theta and grad theta. And then you can think of a process in which the time derivatives of these variables can be set arbitrarily. Okay? So they can be set arbitrarily. And in the book, if you look at, no, they have given example of how they can be set arbitrarily. So this can convince you, at least give you one example where they can be chosen arbitrarily. Okay, so look at the book. So this all this discussion is in chapter 8 of the book. So what does this really mean, that you can set them arbitrarily? That means for a given f theta and grad theta, you can think of a process in which theta dot is 0, grad x theta dot is 0, but only f dot is present. And that f dot can be arbitrary. Similarly, you can think of a process in which only theta dot is present, but other two time rates are 0. Similarly, only grad x theta dot is present, but other two time rates are 0. So you can independently change the rates. Now, can you see what will be the implication of that? So suppose, for example, you have f dot not equal to 0, but theta dot equal to grad x theta dot is equal to 0. So in that case, the above inequality reduces to rho naught del psi over del f minus p double contraction f dot plus q naught dot grad x theta divided by theta less than equal to 0, right? What do you think? What else can you think of? Now, even in this inequality, f dot is arbitrary. You can choose f dot whatever you want. In particular, you can choose f dot equal to some arbitrary scalar quantity alpha times rho naught del psi del f minus p. You can also choose that. But if you do that, then let us see what's going to happen. So if you do that, you have rho naught del psi del f minus p double contracted with itself. So that's going to give you magnitude of the second order tensor. That means take each of the components, square it, sum it, and then take the square root. So that's the magnitude. So what you get is this square times alpha plus q naught dot grad x theta divided by theta less than equal to 0. Now you see this thing is some fixed quantity. It could be some number, some number. But over here, you can choose alpha, for example, to be a positive number, a very large positive number, so that this whole thing on the left hand side becomes more than 0, right? We don't know what is q naught dot grad theta by theta. Is it a positive number or negative number? We don't know. But whatever it is, you can always choose your alpha to be a very large number so that it dominates, and so the left hand side becomes more than 0, right? So in that case, it will then violate the entropy inequality. So what do you think? When can this be satisfied? When this entropy inequality can be satisfied when alpha is arbitrary? So the restriction then is that the magnitude of rho naught del psi del f minus p, this must be 0, or this p is equal to rho naught del psi over del f. You see, this is, you are able to deduce the formula for the first Piola-Kirchhoff stress tensor in terms of the derivatives of the Helmholtz free energy. So you don't need to have independent function for P. Once you have chosen your psi, then P gets set automatically. Okay, I hope this looks quite convincing to all of you. So likewise, if you proceed this way, what else can you figure out? Similarly, this argument of theta dot, or the coefficient of theta dot, should be 0. Likewise, coefficient of g dot should be 0, right? So the restriction that you are getting now, likewise, you can say, you see, it's such a great restriction, no? So what you're getting is that del psi over del theta, or I'll say eta, is equal to negative of del psi del theta, right? And similarly, you have del psi over del g equal to 0. But this also means psi does not depend on g or grad x theta. Okay, so from the argument of psi, so this function psi hat has just f and theta as argument. But then you see, it means P is also then only dependent on f and theta, because P is from the derivative of psi. So if psi does not depend on grad theta, then P will also not depend on grad theta. And likewise, entropy will also not depend on grad theta. So can you see that the second law is really putting a great restriction? So it says that, so finally what we have deduced is that psi hat has only this functional form. So we have this psi hat, and then we have the formula for P, which is rho naught, or P hat function, we can think of rho naught del psi hat over del f. And similarly, the entropy function is negative of del psi over del theta. Okay. So once you have these restrictions, you can go back to your entropy inequality, and what you see is that it reduces to Q naught dot grad x theta over theta being less than equal to 0. Isn't it? You can come back here and see everything is vanishing. Sorry, you are here. So everything has vanished except for the last term. So what do you get then from here? Theta is always positive number. So Q naught dot grad theta has to be less than equal to 0. So this is what you get from here, because theta is always positive. So Q naught dot grad theta has to be less than equal to 0. So the heat flux vector and the gradient theta vector, the angle between them will be more than 90 degrees. And in fact, a very specific form, you have seen that the heat flux is always, or the conduction is always opposite to the gradient of theta, right? It flows in the direction in which theta is decreasing. So it's opposite to the gradient of theta. So it's exactly opposite to gradient of theta if you have isotropic kind of law for conduction. But if the law is not isotropic, then it won't be exactly opposite, but in a direction such that the angle between the two is more than 90 degree. Okay, so basically if grad theta, if this is the direction for grad theta in a material somewhere, then what the second law tells us that Q naught can only be, the heat conduction can only be here. Okay, so this is all the directions feasible for heat conduction. So it's magical, isn't it, that second law of thermodynamics is able to give us so much of restriction. Okay, so finally what we see is that what all do we need to characterize a thermoelastic material? So to characterize a thermoelastic material, we only need two functions. One is psi hat as a function of f comma theta, and other is the constitutive form for q naught, the function for q naught, and it has dependence on f, theta, as well as grad theta. Okay, so in total, four functions are required. So for any general thermoelastic material, you only need these four functions and everything else gets set accordingly. Okay, so this is a restriction that is coming from field equation, second law of this thermodynamics or entropy inequality. But you know that the constitutive equation has to satisfy several more things like the objectivity, then symmetry, material symmetry, right? So let us now see what is the implication of frame indifference. So the implication of frame indifference or objectivity. So you know that in this case you have to look at two motions, y star and y, and they are related. Y star of x comma t is equal to qt times y of x comma t, right? So for the two motions, we know how psi should transform and how q naught should transform. We have already seen them. Okay, so the first thing, of course, is the temperature. So theta is star for the new motion, theta being a scalar quantity, and from physics we know that it should be objective. So that means theta star x comma t would be same as theta of x comma t, isn't it? So in both the motion, the temperature theta should be same. And we know for f star that f star is equal to q times f. This is we know. And if you talk of psi, what should, how should psi and psi star be related? They should be the same, right? Because psi is also an objective quantity, and being scalar, psi star should be same as psi. Now what will psi star be? Psi star will simply be that function psi hat. See, the function is not changing because this function is going to hold for every motion. So it will hold for y as well as y star. So psi hat function or psi hat star function, they will be same. So I'm just writing psi hat. But psi star is the actual value in the motion. So psi star will then be function psi hat evaluated at f star comma theta star, isn't it? But that's equal to psi hat of qf comma theta. Okay, and this has to be equal to psi itself, right? We know that because from here you see, but psi is simply function psi hat evaluated at f comma theta. Okay, so the implication of objectivity is that this function psi hat must be such that psi hat of qf comma theta is equal to psi hat of f comma theta, and this has to hold for all q and all f. So for a given f, it has to hold for all q, where q is the rotation tensor. Okay, rotation tensor. For all rotations, it has to hold. So what's the implication of that? It's really going to put a huge restriction. Can someone tell me um, how can we proceed from here? So this is the mathematical restriction. What will then say about the function psi hat? So if you evaluate psi hat at f or at qf, it has to give you back the same thing. So does it tell you something about the function psi hat? See, this function can return the same thing only if psi hat actually depends on something which is not changing when you change f to qf. So basically we have to think of what is it that is not changing when f changes to qf. So what is remaining invariant? So what is invariant? Because the psi hat must depend on that invariant. Yes. So I think Vikram Parmar, for example, says that the psi hat should then depend on u. So what he means is that u is invariant here. And indeed that is true, because you see when you do polar decomposition of f, you get r times u. And when you do it for f star, you have q times r times u. So here your r star is actually qr and u star is u. So r star is changing, but u star is not changing. It is u which is invariant. So that means this function psi must depend on just u part of f, not on the rotation part of f. Isn't it? And this kind of also makes sense. You remember what was the physical meaning of r and u? So you see psi hat is the stored Helmholtz free energy. So basically what we are saying is that psi hat only depends on u and theta. So you have this body and at a point you have big F. So what does R do? What does U do? R is only responsible for rigidly rotating the local volume, right? Local line elements. They only rigidly rotate due to this local rotation big R. Whereas it is U which is responsible for generating strains, longitudinal strain, or the change in angle, or the change in volume, or the change in area. All that is coming because of you. Big R is only responsible for changing the orientation, right? So that should not affect your energy. And that is what you're seeing here, that psi hat is only dependent on the u part and not on not on the rotation part of F. Okay, so that's indeed a very nice restriction, isn't it? And you also know that it is same as square root of C, isn't it? And actually C is also not changing. When F changes to QF, C star, which is F star transpose F, that's equal to C, right? So it's easier to say that psi hat has dependence on C and theta. Instead of saying that it depends on U, for the mathematics purpose, for taking derivatives, it's easier to write psi hat as depending on C, because C is F transpose F. You're not getting any square root, whereas in U, you have a square root of C. So while taking derivative, for example, you have to take the square root, derivative of square root, so that's a bit complicated. Okay, so this is more easy to work with. Similarly, what do you think for the Q naught function, which had f theta and grad x theta? And you know that this Q naught hat, because um, it's a referential heat flux, isn't it? And how does Q naught transform? Does anyone have any idea what happens to Q naught star? Is Q naught objective function? Anybody, do you recall? Is Q naught an objective function? Q was an objective function, but what about Q naught? So yeah, it's not an objective function. So Q naught and Q naught star are the same. If it were objective, Q naught should have changed to Q times Q naught. So having seen that it's the same, we'll simply write it as Q naught hat of F star, theta star, and grad x theta star. Okay, which is actually same as Q naught hat of Q times F, and theta star is same as theta, and grad x theta star will also be same as grad x theta, because you see theta star is same as theta, and the gradient here you are taking with respect to reference configuration, and reference configuration does not change when you go from y to y star. So grad x theta also remains the same. Okay, so from here again, the functions, so you have three functions here, and each of the three functions, you can again think of their scalar functions and then apply the same logic as for psi hat to say that they will also depend just on the C, the right Cauchy Green tensor. Okay, so basically Q naught hat is then also only dependent on C, theta, and grad x theta. Okay, so this is the implication of objectivity. So what are the functions which are ruled out, for example? So if you say you have the function psi hat of f comma theta comma grad theta, and you say that, okay, let us choose this function to be trace of f, that this is ruled out. So this is ruled out from objectivity, because then psi hat of qf, so trace of qf is not the same as trace of f, right? So such a function is ruled out. But if you assume that psi hat of f theta grad x theta is equal to trace of f transpose f, f transpose f is c, so dependence on c is allowed. So this is perfectly fine as far as objectivity is concerned. Okay, having seen this psi hat, let us try to see what will Piola-Kirchhoff stress tensor, for example, look like. So Piola-Kirchhoff, we know that it is rho naught del psi over del f, right? Something that we derived from the second law of thermodynamics. But psi hat depends on c, so we'll say it is rho naught del psi hat over del c, and then some del c by del f, right? Using chain rule. But we don't know, you see, this is a fourth order tensor. This is a fourth order tensor, whereas this is a second order tensor. So how are they going to be multiplied so that it gives you a second order tensor? So we don't know that. So I have just written it abstractly. So to see it more clearly, we can then use index notation. So I have always said, whenever you don't know how tensors are getting multiplied, then you just go back to initial notation. So I'll say that Pij is then rho naught del psi hat over del c im into del c im over del f mj, isn't it? So that's Pij using chain rule. So we have to now think of what will be del c im over del f mj. Now c, we know it is f transpose f. So what is CIM then? So CIM will be FKI into FKM, isn't it? So what is then del CIM over del FMJ? So del FKI over del FMJ into FKM plus FKI into del FKM over del FMJ, right? And you see that f is not symmetric, so fkm is not equal to fmk. So what is this then? Del fki over del fmj. So you are taking the derivative of component of f with respect to another component. Now you can think that each of the components are independent of each other. So when you take the derivative of one component relative to other, it will be 1 if they are the same and 0 if they are not the same. So that means you can write it as delta km into delta ij, which means k has to be equal to m and I has to be equal to j. Then only it gives you 1. Otherwise it is 0. Because it's the product of two Kronecker deltas multiplied by fkm plus fki into delta km into delta mj. Okay, but then this you can also write it as, see, this is delta km into fkm. So you have summation over m, or you think of it as a summation over k, then what does this become? Anyone? Okay, I think we are making some mistake here. Can someone tell me what's the mistake? Okay, here this should have been Fij, no? Nobody said to me. But also no, this is, see if you, here right now it was Fmj, but then M is appearing three times. One, two, three. So this is not allowed. An index cannot appear more than twice, right? So we should have written it as rho naught del psi hat over del C, let us say Mn into del C Mn over del Fij. So this is how we should have written it. So, okay, so we have to do everything again. So I have to find out what is Cmn. So that's going to be f of km into f of kn. Okay, and then we take the derivatives. So you have to be also attentive and tell me when I'm making mistake. So this implies del Cmn over del Fij. So that's del Fkm over del Fij into Fkn plus Fkm into del Fkn over del Fij. So this is then delta Ki delta Mj into Fkn plus Fkm into delta Ki into delta Nj. Okay, and then you look at these two, you have summation over K, but since it's Kronecker delta, so the K summation will go away and you have to replace K with I. So it becomes delta Mj into Fin. And likewise here, you see these K's are here, so it becomes Fim into delta Nj. Okay, so you can come back here and write it as rho naught del psi hat over del Cmn into delta Mj Fin plus Fim delta Nj. And furthermore, you have this M appearing here and this N is here. So this is then going to become rho naught del psi hat over del C Jn. Okay, I should write it below. So this is rho naught del psi hat over del C Jn into Fin plus del psi hat over del C Mj into Fim. Isn't it? Now what do you think? What can we do from here? So this is Pij. So what is the tensor P then? So isn't it rho naught Fin and then del psi hat over del C Nj, but the transpose, plus del psi hat, sorry, again Fim into del psi hat over del C mj. So don't you see that it is same as rho naught? I mean, if I want to go back to tensor form, it's P equal to rho naught F into del psi over del C transpose plus F into del psi over del C. Isn't it? But you see, psi, you are taking the derivative with respect to C, which is a symmetric tensor. So del psi by del C should also be symmetric, right? Del psi by del C ij should be same as del psi by del C gi, or Cij is same as Cji. So this is same as del psi by del C. So what you get finally is this is equal to 2 times rho naught F into del psi by del C. Okay, so that is your P. 2 times rho naught into F into del psi over del C. So this is the implication of what? Second law of thermodynamics plus objectivity. Second law told me that P is the derivative of psi with respect to F, and objectivity said to us that psi depends on C, and therefore together this is what we are getting for P. Now let us see about the angular momentum balance. How does it look like? Do we get some extra restriction if you incorporate angular momentum balance? So we want to look at PF transpose, right? So PF transpose should be symmetric. That is the angular momentum balance. So PF transpose is then what? 2 times rho naught into F into del psi over del C into F transpose, right? So what is the transpose of this quantity? PF transpose transpose. Take the transpose on the right hand side and what do you get? You get back the same thing, isn't it? You see, you're getting back the same thing. So what this tells us is that A and B gets automatically satisfied. So second law of thermodynamics, or entropy inequality together with objectivity, ensures that angular momentum balance is automatically satisfied. So if you choose a good constitutive relation, which is in consonance with entropy inequality and objectivity. So if you choose such a good function, constitutive function, then you don't have to bother about angular momentum balance. It is getting automatically satisfied. You see, this is again magical.
Sir, we have written to characterize a thermoelastic material, 4 functions are required.
Yes.
So we could finally reach to only psi hat and q naught. So
Yes.
p hat and entropy also we are including that we are telling 4 functions.
No. Psi hat has got 1 and q naught has got 3 because q naught is a vector, no?
Okay, that's it.
4 functions because p is derivable from psi, no? P is
Yeah,
not
understood.
psi
Yeah,
by
p and entropy depends on psi. So we have
yes.
3 from q naught and 1 from psi. So total 4.
Exactly.
Okay. And sir, how we have equated the q naught as a vector to q naught itself for all the star quantities, like for objectivity?
Yeah, so we said that Q naught star is equal to Q naught, and this is something we had derived in one of the previous classes,
Okay,
right?
okay.
So Q naught is not an objective quantity. It does not change when you go from Y to Y star.
Because it is in the referential one, so it
Yeah,
remains.
right. Yeah.
Okay.
And we had
So
derived it actually. If you see the derivation, we have derived it.
Okay, okay, I
The
will.
vector Q, the
Uh,
heat flux, actual heat flux vector, it does transform, but Q naught does not transform.
okay, sir. Okay. Thank you.
Sir,
Yeah.
there should be one transpose mode FIM when we bring it from right to left.
Oh, you think so?
In last set, there one transpose I think.
Which one?
PIJ का last term.
You mean here?
Yes sir, yes sir.
But I don't see any transpose.
When FIN comes from right to left, there is a transpose come na?
No, no, no.
First term. तो
No, it
इसको भी
won't.
मैंने
See, Fin is a scalar quantity, no? And
ओके
del psi by del Cjn is also a scalar. So scalars you can move anywhere without doing any transpose.
अच्छा अच्छा ओके सर.
Yes.